Hello everybody. In this lesson we will talk about the man you see on the picture. It is Mr. Coulomb, and that's the topic of today, Coulomb's law. This is chapter 18.5, Coulomb's law. So we have learned in the last lesson that if you have two objects, they can attract each other or repel each other. So for example, if you have a positively charged object and a negatively charged object, they will attract. And Coulomb has investigated on how big the force in between these two objects is. Well, some sort of it makes sense to assume that it depends on the charge that this object has, Q1, and also on the charge of the other object. It also makes sense that the spacing in between these objects matters, and that's true. So we can here draw the distance between center to the center of these two objects, and we call this distance r. And Coulomb's law then says that it is proportional to Q1 times Q2 over this r squared. And there has to be some constant in between, some proportionality factor, which very often is given as a k. This is Coulomb's law. And it tells us how strong the forces are. It's very similar to the law of gravity. And also here, object 1 is attracting object B, B is attracting A. So therefore there is no vector symbol on this F, because we always have two forces, one on object 1, which then is F1, so to say, and F2, the force 2 on the second object. This factor K was found by experiments, and it is given to be 8.99 times 10 to the power of 9 Newton meter squared divided by Coulomb squared. So you find this number in the formulary usually, as well as Coulomb's law. Let's do an example. So let's assume you have two charges that are charged here with 0.05 microcoulombs each. And they are separated at a distance of 10 centimeters. What is the force that one charge experiences to the other one? Calculate. The answer is, we just use here the formula. It is K, which is 8.99 times 10 to the power of 9 Newton meter squared over Coulomb squared. Then charge 1 is 0.05 times 10 to the power of micro is 10 to the power of minus 6. Same thing again. You could also take that to the power of 2, of course, and 10 centimeters is 0.1 squared meter squared. And if we now look at the units, you see that we have here coulombs and coulombs, which simplifies with the coulombs to the second, meter squared, and we are left with newtons. And of course, a force has to be in newtons. And if you put this to the calculator, you will find the answer. I have calculated this and it is 2.25 times 10 to the power of minus 3 Newton, or 2.25 millinewton. That's it. However, in some formula books you will find Coulomb's law given in a different version, and we will quickly have a look at this version. Of course, it's the same, it's just different constants that are used. So let's have a look at this second version. You find this version to be Fc for Coulomb to be 1 over 4 times pi times epsilon 0 times q1 times q2 over r squared. So the only difference is in front of q1 and q2 and r squared, there is this new unit. And the epsilon is given to be here 8.85 times 10 to the power of minus 12 Coulomb squared over Newton times meter squared. And we can check if this is true. So K has to be the same as 1 over 4 times pi times this epsilon 0, and we can fill in the number, and you can here do that yourself. So Coulomb Newton meter squared, and you will get these 8.99 from above. Times 10 to the power of 9 Newton meter squared over Coulomb squared. This epsilon 0 is, as I have now said, very often referred as the epsilon 0. Epsilon is this Greek letter that you can see here, but in reality this number is called permittivity. Although no one actually uses that word, so everyone is speaking about the epsilon 0 here. As I said, nothing to worry about, just a second version, and we will see later why it makes sense to use this second version in some cases.